In this video, we'll be looking at exercise 7.1 from chapter 7. We have a data set with V basically interpreted as X, and we have Y. And we want to fit a quadratic polynomial. In part A, we have to find the coefficients for the quadratic polynomial. We know that there are three model parameters, C1, C2, and C3. We want to find the standard deviation for each parameter, t ratio, the correlation coefficient r squared, and basically using the solution for part A, we want to see which parameters or which model or which term of this quadratic fit needs to be kept and others need to be removed. Okay, so let's dive into the spreadsheet. So we create the V column, the Y column, basically X and Y. We know that we have to create a G matrix, and for G matrix we need V squared, V times Y, V cubed, V4, V times Y squared. We also create a column for Y calc because we want to calculate the residual based on the Y calc, residual squared, and Y minus Y bar squared to get the correlation coefficient. And down here we have the sum of each column. So we can create a G matrix. The first one is a number of data points. We have 5 data points here. This one is X times 1, and this is basically V, right? So here's just sum of the V, and here's sum of the V cubed. So this is V times 1, and this should be actually V squared. Sorry, this should be V squared. Yes. So this is sum of V, this is sum of V squared, and this is symmetric. This one is also sum of V squared. This one is sum of V to the 4th power, which is 138. And this one is sum of V times V squared, which is V cubed. Right. Okay, so we have a G matrix. On the right side, we have Y times, well, actually, this is sum of the Y times V, right, which is this, and then this one is sum of V squared times Y, which is this one. That's right. So we have G matrix. We have the right-hand side. We can go ahead and calculate the coefficients. So here's the coefficients. We can also calculate the G inverse using the matrix package. We go ahead and calculate the Y calc now. So every Y is going to be the constant term plus the linear term times V, and then the quadratic term, or C3 times V cubed. So this is Y calc we just drag down. We find the residual, which is the difference between the calc and the exact value or the experimental value. Then we can calculate the residual squared. We sum them up. We get this, and then from here we calculate the residual squared, which is the sum of residual squared divided by sum of Y minus Y bar. By the way, Y bar is also calculated here, which is sum of the Y divided by 5. Right, so just to double check, that's the sum of the Y plus, well, divided by the number of data points. Okay, so we have Y bar, we subtract every Y, so this is this Y, not the calc, just the experimental value for Y. Okay, minus Y bar, and then we calculate this for every data point, we sum them up, and then for correlation coefficient, we divide a residual squared divide by Y minus Y bar squared. Okay, so now we can go ahead and calculate the G inverse SE, which, if you remember, was sum of residual squared divided by the degrees of freedom. In degrees of freedom here we have 5 data points minus 3 model parameters is 2. So we get SE squared, and we can go ahead and calculate G inverse, which was SE times the inverse of G. Okay, so, well, G inverse is the inverse of G, and then we can calculate the standard deviation matrix, or the variance matrix, which was SE times the G inverse. So we go back just to make sure that we are on the right track. SE times G inverse gives us the variance matrix, I have to go up. Yes. Well, SE squared. So SE squared times U inverse gives the variance matrix, and the square root of the diagonals are basically these three. And then from these three, we can get the t ratio, which is the standard deviation, by the coefficient. So in other words, I'm sorry, the coefficient divided by the standard deviation, so that's C12 divided by C15. Well, F12. F12 divided by C15. Okay? And then we can go ahead and calculate the C ratios for others. And we see that two of them are below 2, right? The last one and the first one, but we're going to start from the smallest. The smallest is C3, so we're going to drop C3 and recalculate everything. Okay, so for part A, we actually don't have to do this. For part A, is just the values of C, or the ratios, and R squared. We have to also the plot. So here's the plot of the data points with the trend line, and you know what to do. So you have to right click on the data points. You go to add trend line, and because this is linear, it's a quadratic fit, so you have to click on polynomial at degree 2. Okay, and make sure you go to options and display the equation on the line. Okay, so then here's the well, actually, let me see. I think you also can include the R squared in there. So let's see, you can also display R squared, which is the correlation coefficient. If you click on both of them, then you get R squared as well as the equation. Okay, you can also plot the residual. So this is residual against the x value. Residual is just this column. And some of them are plus, some of them are negative. Okay, so for part B, we'll have to skip part B. For part C, we know that we have to drop the third model parameter, which is C3. So we're going to drop C3, right, because that is the smallest one, less than 2. So in part C, I drop that one, and I'm going to show you only the last result. So we're going to have the intercept, or the constant term, plus a linear term. And if you do that, you follow the same procedure as we did before. Right now we have, again, 5 data points, but this time when you do the fit, you want to include the constant term and the linear term. You have to calculate the G inverse, standard deviation, T ratios again. And you see that this time both T ratios are bigger than 2. So that means you have to keep both terms, the linear term and the constant term. Okay? So that means in part A, you should not drop both of these. You only drop the smallest one first. You calculate T ratios again, like this, and you see that in fact the first term, or the linear term, still needs to be included. So, okay, so now we're going to have the constant term and the linear term. I think that is it. So that was part C. For part D, we have to fit a 4th degree polynomial and see if that is a good fit or not. So here's a 4th order polynomial. You can go ahead and do that with trend line. Make sure you put 4th order polynomial. And so in this case, you get R squared equal to 1 exactly. And we know that the correlation coefficient has to be between 0 and 1. And the bigger, the better the fit. So it looks like this fit is excellent. It actually goes through all the points. But there's a problem with it, because this looks like overfitting, right? I mean, if you have like 5 unknowns, or 5 unknowns for the coefficients, right? So there's 1, 2, 3, 4, 5 unknowns, and you have 5 data points. You can easily go ahead and calculate all those 5, and that guarantees that the line goes through the data exactly. But the problem with that is, if I get maybe the 6th experimental data point, from the experiment again, that's not going to be along this line. On top of it, if there's a little bit of error, to each of these data points, then we're basically having a line that goes through something which is not really right. I mean, if there is some uncertainty, for these points, you don't want your line to go through all points, because there is some discrepancy there, right? So there's some variation for every point. So we call this overfitting, and as a result, this may not be a good fit. Okay, so usually the model should be smaller. The number of unknowns in the model should be much smaller than the number of data points. If you have like 5 data points, most likely you can go with linear. If you have like 100 data points, maybe fourth order polynomial is good. Okay. Okay, we can go ahead and also look at problem 7.4. We have an equation like this, and we want to fit to some synthetic data. So this time you see that the fit doesn't have, like polynomial form. It's like it has log x, has exponential, so it's a bit more difficult. Anyway, so here's the data we have, and the question is which model parameters we have to keep. Okay, so the solution to this is we have to convert the problem to be something like this. Instead of having log x over x squared, I'm going to lump that into a parameter, call it z2, and an exponential of minus x, I'm going to call that z3. And then, of course, z1 is the coefficient of this constant, just c1, so the coefficient for that is just 1. So I'm going to create columns for z1, z1 times z2, z1 times z3, z2, 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 z3, and z3 squared. We also create z2 times y and z cubed, well, z3 times y. The rest is pretty much like as we had before. The only thing is we don't have x or x squared or x cubed. In here we have z1, z2, z3. Okay. So with this, we can go ahead and create the G matrix, right? So G, the first one is going to be sum of Z1, which is just 21, because we have 21 data points. This one is Z1 times Z2. This one is Z1 times Z3, which is this, this one, right? So this is Z1 times Z3, you see that? And so with this constant, we can go ahead and create a G matrix. In the right-hand side, the coefficients you get should come to be something like this. You can go ahead and calculate the R squared as before, SE squared, and this is the correlation coefficient. And then you can go ahead and calculate the T ratios and see that the T ratios are, one of them is less than 2, the other two are bigger than 2, so we have to drop C1. Okay, so this one needs to be dropped, and after we drop it, basically means that in our table, we're going to have a Z1 to be 0. So because we don't have Z1 anymore, and all the coefficients that have Z1, like Z1, Z2, Z1, Z3, all of these become 0. In other words, this part of the matrix will be gone. Oh, I'm sorry, so this and these two. So basically this, in the first line, the first column is going to be gone. So we're going to have only this corner. And so that's what we have. Now this is a fit for two model parameters, just C2 and C3. We don't have C1 anymore. With this, you can go ahead and calculate, the coefficients. On the right-hand side, the coefficients, and you find that the T ratios now is going to be about 3,000. So both of them are much bigger than 2. That means we should keep both of them. We should not drop anyone. Okay, so that's basically a quick review of the solution for problem 7.4b. I just emphasize again in here, because there's no polynomial, we have to lump them into parameter like z, which should look something like polynomial. So here we have c1 times 1, and that 1 is going to be renamed as z1. c2 times whatever, and this whatever is going to be z2. And then c3 is going to be, well, c3 times exponential, and this exponential is lumped into z3. Now think of this as we have z1, z2, z3. We follow the G form or the G matrix, which was z1 times z1, z1, z2, z1, z3, and z2, 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 z3, and z3 times z3, basically. And so we can calculate all these, the elements above the diagonal, as well as the diagonal. So we want to calculate these 6 terms, which are basically, so this is the first term, second term, third term right here, and then on the diagonal, and this is the third term on the diagonal. So that's how we can basically construct the G matrix and go ahead, find the T ratios, and figure out which one is bigger than 2, which one is smaller than 2. Okay, I hope this is useful. Thanks all for watching.